This is lesson 5 in Unit 5 on curve sketching, where we're going to look at a procedure for making relationships and connecting those relationships between a function, its derivative, and second derivative. In this table, if you think about the language that goes symbolically, f prime of x is greater than 0 means a derivative is increasing, or less than 0, a derivative is decreasing. So when the first derivative increases and the second derivative is positive, our function graph is concave up and increasing. It would look like that. And in each one of these boxes, this is the sketch of the general shape of the curve when we meet each of the conditions, sort of like a Punnett square, isn't it, for math and the shapes of graph. In this example, I've already pre-drawn the first derivative test and the second derivative test. It's a long lesson, and I'm trying to shorten up your video watching time. So reading across the first set of conditions, if the first derivative is positive on negative infinity to negative 1 and 3 infinity, and the first derivative is negative inside 1, negative 1 and 3, then we would have a graph that increases and then decreases. So there's a maximum at negative 1, and then decrease to increase would mean a minimum at 3. In the second line, we've got the second derivative is positive from negative infinity to negative 3, so that's reflected here. That tells us the function graph is concave up in this section, and also concave up in negative 1 to 3, but concave down between negative 3 and negative 1 and 3 and infinity, so concave down. This last statement says that we've got horizontal asymptotes at both extremes, one at negative 4 and one at positive 4. So if you want, pause the video and try to draw that graph based on this information we have. Okay, if you did pause the video, this is the type of graph that you would end up with based on all of those givens. We've got a horizontal asymptote at negative 4, one at positive 4. We're increasing, have a point of inflection at negative 3, then decreasing. I'm sorry, not decreasing, then continuing to increase until we get to negative 1 where there's a relative max, and then we begin to decrease, but we're concave up in here in this section. We have a min over here at 3, and then again concave down until we get to 4 as the extreme at the other end. Okay? Let's go on to the next example. Oh, well, first we're going to stop and look at the function behavior chart. As you go through the course, you want to be familiar with our vocabulary, and I've tied some symbols to that vocabulary, which helps us curve sketch all through this section and on into Unit 6 when we're looking at accumulation. So we want to be aware of that vocabulary. I see increasing. So if a function's derivative is increasing, the function graph is concave up. So just learn to read that table. Okay, here's some key concepts. Can you sketch a possible graph of a function given the derivative? So we're looking at a derivative, and I'm going to call that 0 and this 0 A and B, and I'm going to call that low point or that minimum C, okay, which is happening at 0. Actually, I guess we don't really need to call it C, but we'll make a note of it that it's a minimum. And then reading the graph based on that table that we just looked at, we've got the derivative graph is positive here. It's above the x-axis. You could either write positive, the derivative is positive See, the derivative is positive, the function is increasing. The function increases. Then the derivative is negative in between a and b because the derivative is below the x-axis. The function decreases, making the point a maximum right there. So I've got a zero derivative here and a zero derivative here. And then after b, the function, the derivative is above the x-axis, so the function's increasing, making b a minimum. Then the extrema on a derivative is a point of inflection on the function. So this is a minimum on the derivative graph, and my function is going to have a point of inflection right there. The graph is decreasing. The derivatives are negative values. See how the derivatives appear to be negative slopes? So the function is going to be concave down and concave up on the other side. So we can easily sketch that graph out here. Let me erase these. Now it doesn't really matter where you translate that graph. I just know that I need a maximum at A and a minimum at B and a point of inflection at 0 somewhere. And that my graph has to increase, concave down, and then at 0, concavity changes, and we're going to be decreasing. At B, it's a minimum, and then concave up. So I missed my marks just a little bit, but you get the general idea. So we have a maximum at A, a point of inflection on the y-axis, and a minimum at B, and we have followed those sign charts. Guess I need to look at 2 pages here. So we'll go to the dual window view and answer the questions that go along with this. Zeros of the extreme of f prime may be extrema on the function graph. And extrema of the derivative, like this minimum, are possible inflection points. And when the derivative lies above the x-axis, then the function would be increasing, and it would be decreasing. The function would decrease when the derivative lies below the x-axis. When the second derivative is positive, the first derivative is increasing, and the function graph would be concave up, and the opposite would be concave down. If the first derivative is decreasing, like this, decreasing, then the second derivative is negative, so the function is concave down. Okay, in this next example, we're going to connect, this is kind of a long example. First, we're looking at this graph and supposing that it is a function graph. This is the graph of y equals f of x. We want to know on what open interval is the function both increasing and concave up. So if we take a look at this graph, the graph is increasing and concave up at -5 over to -2, and also increasing and concave up right there between 4 and 6. Then on Roman numeral 2, on what open interval is the function both decreasing and concave down? So it's decreasing and concave down, I would say right in here. That would happen on -1 to +2. Where would the function graph have inflection points? Well, inflection points are where concavity changes. We're concave up, and then we're concave down. So -2 is a point of inflection. Concave down to concave up. So right here at +2, and then it looks like it's 6 would be the next point of inflection. Now, part B, we've got to change our thinking. Let's consider that we're not looking at the function graph any longer. Now we're looking at the derivative graph. So our thinking switches and our language switches. On the first question, on what open interval is f decreasing, and let's justify that. So we know that f decreases where the first derivative is negative. And negative means it's below the x-axis. So it looks like between 2 and 6. So let's say where f prime of x is negative, that happens on 2 to 6. So I justified and I stated the interval. On a free response, we'd want to write it a little more formally with a full sentence. At what x values does the function have a local maximum? So at what x values does it have a local maximum, and justify that? Well, we know where the derivative f prime changes from positive to negative, or we could say we could have a maximum where the graph, the derivative graph, changed from increasing to decreasing. So either one of those would work. So let's say changes signs from f prime changes from positive, I'm going to abbreviate here, to negative. F has a local max. I'm just going to say a max. And that would happen where? Changing from positive to negative. So above the axis to below the axis, right at 2, at x equals 2. On the next part, on what open interval is f concave down? How do you know? Well, f would be concave down. F is concave down where f prime decreases. Where f prime decreases. So where does that happen? Where f prime decreases. So that looks like right in here. -8 to -5, and then -1 to +4. So 2 different places, from on the interval from -8 to -5, and on the interval from -1 to +4. Roman numeral 4, at what x values does f of x have an inflection point, and we need to justify that? Well, we learned in the chart that we would have an inflection point where the derivative graph has a max or a min. So at -5, at -1, extrema of the derivative are points of inflection. And then to justify that, we would say at x equals -5, f prime changes from decreasing to increasing. So where f prime changes from decreasing to increasing, we're changing from concave down to concave up. Where else does that happen? Here too, right? Decreasing to increasing. So at -5 and +4. And then at -1, f prime changes from increasing to decreasing. So we have 3 points of inflection. At -5, at +4, and at -1. Then into part C, we have to switch our thinking again, once again. So let's erase this. Now suppose that the same graph is really the second derivative graph now. And what open intervals is f concave down? So we have to change our language. We're not talking increase and decreasing now. We're talking positive and negative. So where f prime, where the second derivative is negative, f of x would be concave down. Negative means, in this case, below the axis. On 2 to 6, on that interval, f is concave down. And then finally, at what x value does f of x have an inflection point? We would have an inflection point where the second derivative is 0 or does not exist. So we don't have any cusps or corners on this one. We only have zeros. But also, the second derivative has to change signs. Changes signs from positive to negative. I'm going to abbreviate here. Where does that happen? Let's see. So the second derivative is 0 right there and right here. Oh, what happened? And right here. The second derivative stayed positive through -5, so this one is not a point of inflection. But here the second derivative is 0 at 2, and to the left the second derivative is positive and then it's negative, so that happens at 2. And also when it changes, and the second derivative changes signs from negative to positive, and it's 0 at x equals 6. Okay, so that was a big example. We covered everything. Just changing the vocabulary there. Oh, we're still in 4, example 4. Suppose the graph below is the graph of a function y equals f of x, and on the same axes, sketch and label a possible graph of f prime and do that in red. So just to save time, since I'm not very good with writing on my tablet, I created a sign chart here below so we can read that. F prime at -8 is above the axis. Wait, did they tell us this was a derivative graph or what? Suppose that we're going to sketch the derivative graph. So f is decreasing. F is decreasing to -5. So the function decreases, then the function increases, then the function continues to increase, decreases all the way over to 4, and then increases through the end. So I transferred that language for function behavior, increase and decrease, to the derivative is negative, positive, negative, positive, and so forth. Next, I looked at the rates. So thinking of the rates, if the second derivative is positive, the function is concave up. So I saw that the graph was concave up all the way to -2. And then the function was concave down to +2, and then concave up, and then concave down. So taking that language, I'm cheating a little bit. I'm going to draw the graph. Taking that language and transferring that over to a graph, I have a picture that looks similar to this. So the function was decreasing, so my derivative had to be negative down here below the x-axis. And then at -5, it had to be above the x-axis. But notice how the function, the slopes were increasing till they got almost vertical right here, and then they stayed vertical, but they slowed down to 0 right here. So I had to come rapidly back to 0 on the x-axis between this point and this point. So we made this a corner or a cusp, if you want to call it a corner or a cusp. Okay. And then just following that graph, we had to be decreasing and then increasing from 2 to 4, and then all the way to 6, increasing and then decreasing to get that function. So we took a regular graph, and in red, our red graph is f prime. Oops. Our red graph is f prime. In this one, example E, in the graph below, we have a derivative graph. Now we're thinking differently. This is a derivative graph, and we want to draw the graph itself. So once again, I've used, where did I think I have a table. Nope. Let's stop. Okay, in this case, f prime, we've got f prime, and we want to graph the function. They've told us that the ordered pair -8, 2 is on our graph, which means for us to draw that function graph, we've got to start here at -8, -2. But first I wanted you to notice on my sign chart some things I see. Maybe you see the same thing. Starting at -8, all the way over to +2, every y value is above the x-axis or on the x-axis. I know that we're sitting on the x-axis at -5 as well. So we could make a little note of that. Okay. So what does that tell me? My graph is going to be increasing everywhere until we get over to +2. Then the graph has to decrease. And then after 6, we're back to increasing. Now, we also said earlier that the second derivative would have points of inflection at max and mins. Well, here's a max, here's a min, here's a min. So these are points of inflection on our function graph, right? And this is going to be like maybe a little corner or something, because the slopes are going straight up and then straight down to 0 again. So where there's 0, there are points of inflection, or potential points of inflection, where the graph changes from positive to negative, negative to positive, negative to positive. Okay. And again, just for speed's sake, I'm going to show you the graph I drew with my tablet turned off. We'll pull that up there so you can see the graph I had. Okay, I started at -8, -2, and I had points of inflection those high and low points. And you can pause the video here if you need to try on your own, or just to copy my picture. Trying to save us some time. Here's 5 guidelines. I'll save that for you to read later so we don't make the video too long. Things that we've been doing. In this case, we're going to expand g of x and find the x and y intercepts. I'm just going to write this up here. So I multiplied out that binomial and then multiplied by another binomial and found that our x-intercepts, just looking at the function, one x-intercept is at -2. We have duplicate roots at 1, 0, which means if the multiplicity is 2, the graph is just going to touch and turn around. We learned that in Algebra 2 and Pre-Calc. If you put a 0 into the expanded form, we have a y-intercept at 2. And taking the first and second derivative, the first derivative is 3x squared minus 3. So factoring out a 3, we have x squared minus 1 is 0. Dividing by 3, our critical numbers for first derivative are -1 and +1. And for the second derivative, our possible point of inflection would be at 0, or the critical number of the second derivative. Then complete a sign chart. So G prime, let's see, G prime sign chart at -1 and 1. And our function, think about it, it's a polynomial, so the domain is all reals. And substituting numbers into our first derivative here, we have positive, and then negative, and then positive. Whoop, positive. These are zeros. That tells us our function increases, decreases, increases. Then doing the same thing for second derivative with a critical number at 0, substituting values into our second derivative. We have negative and positive, which tells us the function behavior is concave down and then concave up. Now, you know, on the AP exam, you can't use a sign chart for grading. They have you write a complete sentence. So we would say something along the line that g of x increases on the interval -infinity to -1. Whoop, I don't need parentheses there. Whoop. And one to infinity. And then for the second derivative, g of x, I'm sorry, not second derivative, but for the decreasing, g of x decreases on -1 to +1. And then we want to look at any extrema, determine any extrema. So where's that happening? Well, we got a maximum by substituting -1. So a relative max is 4 if we substitute -1 into our function. And a relative min, I'm giving the value, is 0. The extrema is a y value. Where it happens, they may or may not ask you for the point. Usually not, but you just never know. Okay? And then what are we doing? Complete a sign chart for G double prime. Find the, and oh, we did that already. So we could, again, write a sentence about G is concave down. On negative infinity to 0 and concave up everywhere else. Concave up on 0 to positive infinity, and we had a point of inflection at 0, 2, where x was 0. And then we could sketch that function. It would just be a cubic polynomial. I wrote these earlier. Negative 1, 4 was my max. 1, 0 was my min. This is where we had the turnaround point, the multiple roots, and 0, 2 was our point of inflection. So that function starts like this, has a maximum here, a point of inflection, concavity changes, and off we go somewhere. So a nice cubic polynomial. Okay, going on to what, example 6 now, I believe. Same thing here. I'm going to save time with my sign charts. We've got the graph of a derivative, thinking of this in derivative terms. We need to start our graph at -8, +5. That was an initial condition. So let's look at the sign chart. So here on this next page, you can see my sign chart. I'm reading the derivative graph. It's negative or below the axis right there, between -8 and 5, then above the axis, and then below the axis and above the axis. All of that behavior translates to function behavior. The function's decreasing, increasing, decreasing, increasing. Then I went back and read the derivative graph for second behavior. So the second derivative behavior. The second derivative, these are positive slopes. The first derivative is increasing, so the second derivative is positive. The function graph would have to be concave up between -8 and -3. See how I know that? This is increasing behavior. Increasing derivative means that the second derivative is positive. And then decreasing behavior over to here. So at 1, we're going to have concave down, and then increasing behavior everywhere else after that. Okay? They had to start at -8, +5. So I could do anywhere after that. Let's see. Had to start here, -8, +5. So as long as it started there, and we had a minimum here somewhere, I could make that minimum way down here if I wanted to. Just had to behave, point of inflection here, maximum here. So I guess we would be above, would want to be above 5, right? Or it could be just a relative max somewhere in there. That could be a max. Here's my graph. If you want to stop the video and sketch a picture of that graph, I'll make it larger for you. You can stop the video there and draw that graph. Okay, what do we want to do? Find for example 7. Lost the graph. Here it is. Okay, example 7, where you have a function f prime of x. This is our derivative graph. And we want to answer questions based on the derivative graph. So I believe I need both pages open again. Find the x-coordinates of each critical number for the function based off the derivative graph. Well, the x-coordinates for the critical points are where f prime is 0. So one would be at -4, and the other one would be at 0. So f prime is 0 at -4 and 0. Part B, find the x-coordinate of each relative extrema and label as a maximum or a minimum. So at x equals -4, our derivative changes from negative values to positive values, and where that happens, we're going to have a minimum. I'm going to say because f prime changes signs from negative to positive here. And I'm abbreviating for space. Find the open interval over which the function is increasing or decreasing. Well, where f prime is positive, we know f is increasing. Where does that happen? F prime is positive, so f is increasing on -4 to, we could go all the way through those zeros, -4 to 6. Okay? And where f prime is negative, f is decreasing, and that happens on -6 to -4. All right, part D. Find the x-coordinate of each point of inflection for y equals f of x. And we said earlier that the points of inflection are going to happen at maxes and mins. So a max here, we could say at x equals -2 and at x equals +4, the second derivative. Well, let's talk, they're giving us derivative graphs. So let's say the first derivative. We're going to speak to what they gave us. They gave us a derivative graph. F prime changes from increasing to decreasing, increasing to decreasing, increasing to decreasing at those two places. What's happening at 0? Decreasing, increasing. At x equals 0, f prime changes from decreasing to increasing, right? I'm also thinking about what I wonder if we would need to say something like it's also, for example, at -2, the derivative is 0. I need to think about that. Let's just make a note of that. Now I guess we're good. Let's see. Find the interval for part E. Find the interval over which the function is concave up or concave down. So concave up, our second derivative has to be positive. The first derivative has to be increasing. Where does that happen? -6 to -4, well, all the way to -2. The first derivative increases. And then where? 0 to 4? 0 to 4. And then the concave down, wait, we got to write that up. F of x is concave up. And then the second derivative is negative because the first derivative is decreasing. And where does that happen? That's on -2 to 0 and 4 to 6. -2 to 0 and 4 to 6, which tells us our function is concave down. Wow, this is a long lesson. And then we got 2 more to go. Okay, in this case, we're going to look at a table. I think I've already pre-drawn the graph just for speed's sake. So I looked at the table, I saw 0, 0, 3, 2, 0, 3, -3, and 5, 0. We stopped at 6. They didn't give us a point to stop. I just picked a point anywhere arbitrarily. Then I read what the graph was doing after I had those points on there. I saw that the graph had to be concave down, decreasing, concave up, decreasing, concave down, increasing, concave up, increasing, and ended up with that graph. And we're on to our last one. This function is defined and differentiable on the closed interval from -6 to 5. We're looking at the derivative graph. And let's see, there's a horizontal tangent line at y equals -3 and another one at y equals 2. And we want to find the x-coordinate for the relative extrema on that interval and justify how we know. So I'm going to give us some more writing space. Okay, a little more writing space there. So how do we know? We're looking for where f prime changes signs from positive to negative. So f prime, where f prime changes from positive to negative at -3. So we're changing from decreasing to increasing, if you wanted to say it that way. And from, I'm sorry, yeah, from, I said it backwards. Hold on, that's a mistake. Negative, where f prime changes from negative to positive, or decreasing to increasing, is at -3. and then from positive to negative slopes, F double prime. I like increase and decrease better. I'm rushing through this. Where F prime changes from decrease to increase, and from increase to decrease at 2. So this one is a min at -3. Oh, a point of inflection, I'm sorry. Point of inflection, and this one is a point of inflection on our function graph. Then, oh no, I'm reading B. I messed that up. Hold on a minute. Back that up. Erase that. I was answering part B and part A. We want relative extrema. That's a maximum. I was answering points of inflection in part A. The maximum happens at -5 and +4 because the derivative is changing sign from positive to negative. I started to answer A and then switched over to B. And then there's a min at 0 because the derivative changes sign from below the axis to above the axis. Now we can answer the point of inflection question. Okay, back on track here. Find the x-coordinate for each point of inflection. So this time we're going to say where the first derivative changes from decreasing to increasing. That's going to be right there at -3, and where the first derivative changes from increasing to decreasing that's at +2. Okay, last thing, I'm aware of the time. It's a long lesson. So let g of x be this function, and we want to find g prime of 3. Well, if g prime of 3 is what we want to take the derivative of g of x, that's 3x squared minus f prime of x, and then substitute -3 for each one of our x's, and the f prime of -3, we can get that right off of the graph. So the f prime of -3 is -6. The g prime of -3 is 9 times 3, that's 27. And we're subtracting a -6. So the g prime of -3 is 33. Man, that's a long lesson. One more lesson to go.